All right, looks like it's gonna work. Excellent. Then you just need, we can start working on some practice problems. All right, so quick, here's our quick summary of the enolates. So if we use a strong base but not too strong of a base, we get the reversible enolate formation. So we wind up with both the enolate and the alpha-carbonyl presence of equilibrium. If we use LDA or sodium hydride, we get the irreversible enolate formation. Then if it's a doubly stabilized alpha carbon, we can wind up with just using sodium hydroxide or sodium methoxide, because we have one extra resonance structure. And so that's considered to be complete enolate formation. It's not irreversible the same way that these ones are. But we still can assume that we have none of the protonated alpha carbon left. So with that in mind, let's remind ourselves how these enolates work. Doing some product. So start by drawing enolate form. If you treat any of these compounds with LDA, what do you get? And then down below we have some other practice reactions.
Do practice here.
Filling those out, I'm gonna go fill up my water bottle and then go through.
If you treat it with like a strong base, like sodium hydroxide or sodium oxide, you get the mixture of the carbonyl and the carbonyl, and then if you treat it with sodium hydroxide or LDA, it's an irreversible reaction. You can skip part of it.
All right, so let's start with the enolates at the top. Somebody threw away all the markers that they don't like. So I'll do them a favor, I won't use cheap markers since.
Why is it still 5?
I know it's gotten better, but it's still not great. Alright, so. Reminder that we're trying to, that when we treat these with LDA, the irreversible enolate formation pulls the hydrogen off of the alpha carbon, but it has to have one. So for A, only one of our alpha carbons has hydrogen to remove, so that makes our choice easier. Same for B. Our enolate's gonna look like that. But these are the more reactive resonance structure. Remember, each one of these has a different resonance structure as well, right? It's gonna look like negative charge on the oxygen double bond carbon. Right, so easy enough, I think, at this point, but we're gonna wind up using that a whole bunch today. It can be raised so much cleaner. So what do we do? What happens to the alpha carbon if we treat it with acid and bromine in a base? What did we get in that case? Beta bromine. Yeah, we wound up making the beta bromination or
For active carbon and then alpha carbon, right?
right, so we're going to add the bromine to the alpha carbon. So our final product here still looks like the aldehyde. Right, and the mechanism for this was started by the enol formation, the acid catalyzed enol formation. So we protonate the oxygen, put a positive charge on it, then that has, and then we can deprotonate this alpha carbon by having it, by having the bromine act as the base. We want making the enol and then attaching the bromine right here. Then this bottom one,
With the purity, what does, I was trying to think about that as a.
so purity is usually present because it's a decent base that's aprotic and it's also a solvent. So it's just going to absorb the excess H pluses that we make.
Yes. Okay.
Because we're making an HBr at the same time, right?
Yeah.
And then the second one I had on my slides from before, but I don't think we covered it really. I think it's in the reaction summary. That I threw up there. If I believe it's our way of turning a carboxylic acid into a carbonyl bromide, an acid bromide. But let's double check that one. So anytime you're not sure what we're looking at. Can't read this here. There we go. 120. which is perfect for finding the reaction summary, because then we can go page on 2 pages.
It's not interesting.
So to go from an acid to an acid chloride is on here. Different set of reactions. Alright, so we're gonna leave that one alone right now because it's not on our reaction summary right here. I believe that makes the acid bromide. Because the PBr is gonna act in a similar way to the sulfur in SOCl2. But so as if I'm remembering this properly. When we wind up with this oxygen forming bonds with the PBr. And then we wind up attaching the bromine here and kicking off the oxygen with the phosphorus as the leaving group.
So we kick off the carbonyl oxygen and then the hydroxide oxygen
Turns into the carbonyl. So same basic mechanism.
Yeah.
As the acid bromide.
I 100% safe, so it's very possible.
There it goes.
Yeah.
All right, so let's look at what we get when we have the enolates, these mixtures of enols and enolates. So this is what we get when we treat a combination of carbonyls with a strong but not strong enough base. So if we deprotonate to make the enolate, but we have a mixture of the enolate and the aldehyde is where we see this most, because aldehydes are a little bit more reactive, but ketones to a lesser extent as well. Then what we have is we wind up with a nucleophile and a partial positive. And so we wind up with an addition reaction happening. And this is what's called an aldol condensation. An aldol condensation is when you get an aldehyde and an alcohol as part of your product, kind of like phenol, right? And condensation in the OChem sense just means you take 2 molecules and turn them into 1. You condense them, like condensation means a bunch of water molecules sticking together. So a condensation in this case, a typical condensation, aldol condensation, is when you have the same molecule as both the enolate and as the aldehyde. And you wind up with some combination by the product. And it's basically step 1 of a polymerization reaction, really, because you're still left with something that's a good target for another enolate. And then when that attaches, then you're still left with another target. So under the right conditions, you can actually have this, especially if you manage to make this downhill in energy, which is kind of tricky because you're fighting against entropy for this whole process. Polymerization reactions in general are going to be fighting against entropy because you're taking a whole bunch of separate molecules and turn it into one big molecule. But if you can find a way to do that in an energetically favorable way, that's how we make polymers in general. Right, so if you have a mixture of aldehydes though, you can get what's called the cross aldol condensation, which is what's shown here. The cross aldol condensation just means that, okay, well, if we had ethanol reacting with ethanol, we get the aldol product. If we had this propanol reacting with propanol, we get condensation product. But if we have a mixture of both of those, there's also the possibility that we turn the propanol into the enolate and have it react with the ethanol. Or vice versa, and we get two different products from that. So just because we're crossing them doesn't mean we get the same product for both of these bottom reactions. Right, if I shrink this down so we can see it a little bit better. If we turn our propanol into the enolate and have it attack the ethanol, we get carbon on oxygen 1, 2, 3, and then there's the methyl group. If we switch those, we turn the ethanol into the enolate and have it attack the alpha carbon, or have it attack the carbon here, we don't have a methyl group. So we do get a, even though it's a beta hydroxyaldehyde, it's not the same beta hydroxyaldehyde because of the position of the methyl group. Right, so this isn't all that helpful in terms of synthesis. This seems like this might be really helpful, these aldol condensations, because it's a way you can take two separate pieces and stick them together. It's a way you can modify the carbon skeleton in a fairly predictable way, except for the whole fairly predictable part. Right, because really, if we try to do this in the lab, just the way that it's shown here, we're gonna get all of these products. And they're not gonna be exactly the same ratio. It'll depend a little bit based on thermodynamic concerns, whether or not you're going to preferentially make the ethanol, the ethyl enolate versus the propyl enolate. But either way, it's going to give us close to 25% yield on all these. Right, so if we could find a way to control that, though, that could be a useful reaction. What could we do to try and control which product we make, to only make one product? And we use the same cross-aldol condensation. Frame it a little bit differently. Each of these only made one enolate, right? Why?
Because they only had one hydrogen.
They only had one alpha carbon with the hydrogen, right? So if you use an aldehyde that has no alpha carbons, and an aldehyde that does, then you know which one's going to be your enolate. You're still going to be somewhat limited. So we use benzaldehyde as one of our reactants, and then propanol. That means that we can make this product preferentially. It then goes through a rearrangement because of the resonance structure to make something really close to cinnamaldehyde. I don't remember structure cinnamaldehyde off the top of my head, but I remember that it was an aldehyde with a trans alkene between the aldehyde and the benzene ring, right? I'm not sure if it had that methyl group there or not, but either way, they probably smell like cinnamon, even if it's not cinnamaldehyde. This is going to be pretty close to the same structure. If you use formaldehyde, you get something kind of similar. Formaldehyde doesn't have any alpha carbons, period, let alone alpha carbon with hydrogen. But that still is not an ideal solution, because one, then we're limited in which aldehydes we can use. And two, we're still limited to about 50% yield in this case, right? Because what other side reaction is still happening? Well, leaving off the dehydration that happens here, just in this first step
Oh, it's gonna be the blue reacting with that line with the.
Exactly, the propylaldehyde reacting with the propylaldehyde, the propylenolate reacting with the propylaldehyde reacting with itself. So it's still less than ideal. Any other ideas for how we can do it? Go back to the review slide for a second. We want to put it in a situation where we don't have both of these present.
Yeah, so using
Using LDA. So use LDA, which if you make an irreversible enolate formation, then that opens you up to use to sequencing your reactions too.
do that first.
Do this first and then add the second aldehyde. One of those things where as soon as we say it, it seems really obvious. But coming up with it the first time.
Non-trivial.
So they call that directed aldol addition. It's like first time you see an algebra derivation, like, oh, of course I can just use log logs to separate these two terms. Duh. Why didn't I think of that before? And so if we took acetone, we expose it to LDA, we make the acetone enolate. And then we expose it to our to the target. So the carbonyl that we expose to the LDA first is going to be the one that remains a carbonyl. Because it's going to be our nucleophile for the second step. And so this is definitely one where jumping from if we just were given this, it's kind of hard to picture which one goes where, what we're going to make. But as soon as you draw these, it makes it a lot easier to show what your next step's going to be. Right, because then we have our enolate acting as the nucleophile, which is going to attach to the carbonyl carbon. And the color coding really does help with these too. Right, so we had that resonance structure where the oxygen had the negative charge, but we never really broke that carbonyl on your enolate molecule. We break the carbonyl bonds on the second aldehyde, second carbonyl that's added. Like I said, this winds up being predominantly used with aldehydes because they're more reactive. But really, we didn't make an aldol as our final product. We made a beta hydroxy ketone instead of an aldehyde. It's still considered an aldol addition for the sake of describing these reactions, even though it's not an aldehyde. It was first discovered with the aldehydes because they're more reactive, so it's still called an aldol condensation. Right, and then the last step of the mechanism is just protonate that oxygen. So that looks a lot like any of the addition reactions that we saw for carbonyls back when we looked at aldehydes and ketones, right? Nucleophile attacks the carbonyl, breaks the pi bond, and then you add a proton source to turn it into an alcohol. The only difference here is that we're using enolate as our nucleophile, which is a new trick. So let's try going backwards with that. If this is your product, what was your starting materials?
I meant to do that.
So we know that part of it's gonna have to be that, right?
Yeah.
So this was the compound that we started, we added the LDA to, because that's where the carbonyl started. And then we added the butanol. That one's no better. They always give us these fun colors in our multi-packs of dry erase markers. But unless you're an art teacher, not all that useful. It just looks like I spilled Mountain Dew on the board. It was, yeah. Oh. They are really old and they've been sitting there for a long time, which that makes them.
Yeah.
But yeah, that one.
About the same color, the Power Rangers grew up on, college. During the Halloween party when I was working the handbook.
Yeah, that sounds about right. So, our purple molecule, our reaction looked like. Start with the piece. This still has the carbonyl. And it still has to have that methyl attached to it, because that methyl had to be attached to something. And so if we can break up if we can figure out where the bond was, here's our reactive alpha carbon. And here's the carbon that has the hydroxy group on it. So that's the new bond we added.
Mm.
And so if you slice that bond, that's how you decide what goes on which molecule. Right, so then the red molecule is just gonna look like. Right, because our enolate after step 1 is gonna look like this. Comes in and attaches there. Move the electrons over. Easy enough as long as I'm the one up here with the marker, right? Exactly.
Clear as mud. No, that makes sense. Because you're basically looking at like when you cut the bond, because of the way that the carbonyl is being attacked, the bonds on the hydroxide carbon
Right.
closer to the carbonyl.
And also knowing the alpha carbon is what.
Right.
Getting that negative carbon.
Exactly. The trick is remembering that your new bond is going to be between an alpha carbon and the active carbon with the OH was the carbonyl carbon.
Mm-hmm.
Right, so that's our new bond. Once you can identify what the new bond was, it makes it a little bit easier to work backwards. So let's do it a few more times. So A and C, actually none of these have the OH on them, right? So start by figuring out what the aldol looked like, and then figure out what elimination reaction you needed to do to make the alkene. So when we wind up with one of these alpha beta unsaturated products, if we're, especially if we're saying it came from an aldol condensation, then we just want to work backwards. So we broke that pi bond. And the OH doesn't go on the alpha carbon, it goes on the beta carbon.
Yeah.
Right, so our actual aldol product look like that. Then our new molecule, or our new bond then, is between the alpha carbon and the hydroxy carbon. So we wind up with 1, 2, 3, 4, 5, 6, 7 carbons. Carbonyl on carbon 2. Carbonyl on carbon 6. So we do get the symmetrical molecule. So this kind of makes sense. Because we don't even need to use the LDA in this case, because we only have one possible enolate forms. Regardless of which alpha carbon we look at, that alpha carbon versus that alpha carbon gives us the same enolate product.
What about 1 and 7? We get about 1 and 7 or 3 and 5.
So which of those? I have a whole couple slides. I have slides prepared talking about thermodynamic versus kinetic products again, right?
Because the other cation stability or the anion stability.
So the thermodynamic product would be if we deprotonated carbon 1 or carbon 7.
Yeah, so you're gonna be more stable.
Because the primary carbocations are more stable than secondary. The kinetic product, though, would look like that.
Yeah.
So which one gives us this product, though?
The thermodynamic. Yeah.
Yeah, our new bond is that one right there, right?
Yeah.
Or sorry, no, it's not.
Yeah.
That one. So that's between, and that doesn't have a methyl group attached to the carbonyl here. So it would wind up being this product reacting that way. And then we get 1, 2, 3, 4, 5, 6 carbons in a ring with a methyl group and a hydroxy and a carbonate.
And then push the dehydration reactions, because then it's interesting, there's specifically, there'll be 2 options, right? So where to put that double bond.
Yes.
So how would you control that?
That's a good review question, right? If we're trying to get this, we want to make sure we don't get the Hoffman product. Right?
There's 3 possibilities.
Right. So we want to make sure we don't get the Hoffman products. Out of those 2, though, which one's going to be favored? If our other possibility is putting it right there.
Resonance.
Yeah, we don't get any resonance out of that. So we probably can just use acid catalyzed dehydration. Or if you want to get more specific, we could use oxymercuration was our Markovnikov. No, that's addition. For the dehydration, for the elimination, we want to use a strong base. I went the wrong way. I looked at the addition versus the elimination.
There's a lot.
Yeah.
Sort of all.
For the elimination, we wanted to use a strong base that's not a strong nucleophile, but not a sterically hindered base, because that gives us the Hoffman product. So we go back to term 1 and we go review that chapter to double check. But yeah, just sodium hydroxide or Sodium amide even, or so, would work, because that's a really strong base that's not sterically hindered. We just wanna make sure we don't use something that is too good of a nucleophile, right? Because we don't wanna do a substitution reaction. And we do it at high temperature, because high temperature favors the elimination over the substitution. I kept trying to go with oxymercuration, demercuration,
That's what I was
that's,
thinking that.
like, no, that's the Markovnik alcohol, you don't want, that's addition.
Putting all the concepts together.
Right. Let's do C first, since this one is actually two separate molecules. So for C, if we wind up with the alpha beta unsaturated carbonyl, where the pi bond ends up is your new bond. Right, because this is your alpha carbon, here is your hydroxy carbon. Right, so this was our intermediate. So, and basically we could just use, we can just use heat for a lot of these dehydration reactions, right? Because we really are just gonna lean on the fact that elimination favors making as many products as possible. So we'll lean on the entropy piece, so have a base around, but for the most part, just heating. So then, to make this molecule, we had to start with acetone. Plus LDA gives us the enolate. Then what is it going to attack? Scoot it over so people. Exactly. Again, finding that new bond and slicing it in half is the trickiest part. Yeah, and actually, we probably would just use hydroxide in this case, because then that eliminates any substitution products. We just use hydroxide and heat, because if we did an SN2 with hydroxide,
Right.
we get the same product back. If you use another one, if the you also wind up with the fact that adding a different substitution product also increases the entropy. It's not extra moving pieces, but just a bigger mixture of randomness. Randomness is entropy, right? So by removing some of that randomness, using the same nucleophile as our leaving group, that's gonna save us that step. Yeah, it's better yield. So that's the one that we're breaking. So our intermediate. So that's the alpha carbon. There's the beta carbon. Breaking that, we get 1, 2, 3, 4, 5, 6. No methyl groups. So hexane dial. We don't even need to specify the locates on that one, right? There's no branches or anything. It's a dial that has to be both ends of your chain. And I confirmed this once, but it was now several years ago, so I don't remember exactly what the dial is. But that's actually how dial soap gets its name. It's a dialdehyde, which is what makes it antimicrobial, antibacterial, is the fact that bacteria don't like aldehydes very much. Then again, now that I'm thinking about it, memory is subjective enough, I'm not sure if I remember checking it and I was right, or if I remember checking it and I was wrong. Second guessing that now, so I'll check that at break. Which, I suppose now is as good a time as any, because then we're gonna start talking about other condensation reactions after this. So let's come back at 11.
Might be a couple minutes late coming back. I'm gonna go run to my truck and grab my wallet to pay for this class, the registration person.
Sounds good.
Did you figure out dials?
It was not, it had to do with the marketing, they said it produced around the clock. Odor protection. And so around the clock face is a dial.
Well, I wouldn't be surprised if there are dials or some sort of aldehyde.
They used hexachlorophene. Which, as an antimicrobial, hexachlorophene looks like that. But they later removed that one because it was the reports that it was causing neurological problems in infants. But it turns out that actually the dial itself is kind of an interesting history because it was actually established by a meat packing company called Armour, which my father-in-law still sings their jingle for Armour hot dogs. You can't cook a hot dog near him without him singing about Armour hot dogs. But they had all this leftover beef fat from making hot dogs and sausages. And so they found a way to turn the beef fat into soap. And then they added this compound to it to make it antimicrobial. And started marketing as dial soap. So it was a side product of their main business, which is kind of interesting.
That's interesting.
And to answer your question about the quiz, yeah, anything from the ACS journals works as long as you bring in topics from OChem. Obviously, the easiest ones to make that connection, the ones that are directly OChem. But anything you find interesting.
So there is this one that I found pretty interesting. It was synthesis and identification of three oxazolines in coca.
Okay.
And how adding water to those compounds will create striker aldehydes that will have like more of like a coca malty smell.
Interesting.
So if you add water to the chocolate or to whatever contains,
you get more of a
you get more like a coca scent.
Huh. That'd be a really cool one. Because you
It's
could
nice
talk
too.
about the reaction, and then you can talk about the biochemistry, the scent and stuff like that.
And it has the mechanisms for it, and it even has 2D and one.
I can't think of anything more directly related, and it's got an application too, it's perfect. Right, I'm gonna
All
fill
the
this up
different
again.
kinds of 2D NMR too.
Nice, okay. Teach us something about that too. One more, let's try that, so. Yeah. David said he was gonna be a couple minutes late because he had to run out to asparagus, but, so one other quick note. The, that other reaction from the review slides.
Oh, the PBR.
This is a named reaction, it's actually a fairly unique reaction, it's called that. Make sure I get all their names correct. The Hell-Volhard-Zelinsky hallucination. No known connection between this Zelensky and Ukraine's Zelensky, but he is from the same region of what was then part of the Russian Empire. And then Hell has actually one of the most like Warhammer names I've ever heard. It's Karl Magnus von Hell.
Okay.
That's a Russian or a German name for you. It says start by making the acid bromide, but then it actually does a weird rearrangement where it winds up. it winds up putting a bromine on the alpha carbon to the carboxylic acid. So it starts by doing this, and then it does this weird rearrangement, which we can kind of see that rearrangement. That's just deprotonating the alpha carbon. But then it rearranges again to go back to a dibromo compound and then back to the carboxylic acid. And it'll actually do this. One of the things that's the most sort of idiosyncratic about it. So basically, what the answer for this question as written, would just be put the bromine on the alpha carbon. So I think I grabbed this one out of order because this is more of an alpha carbon reaction than it is actually a carboxylic acid derivative question.
So the bromine replaces the hydrogen.
You put the bromine right here. And I was telling Jerry, it's a kind of a weird, it's a very, very specific named reaction called the Hell-Volhard-Zelinsky reaction. And so the most basic part is, so it starts by making the acid bromide like I thought. But I forgot that it then does this rearrangement to put the bromine on the alpha carbon. And then after that, it'll actually go through a further reaction. And, whoa, you need to do that. You can actually wind up with it reacting with itself to make both the acid bromide and the acid simultaneously. So all of this is, I mean, this all looks like steps we could follow, but it looks fairly convoluted. So you start with the dibromo version with the acid version, and you wind up with the acid bromide and the alpha brominated version of the acid at the same time. So that's more than what I'm looking for in this case. Interestingly enough, though, it does have actually a practical purpose here. This is actually the number one way that they synthesize alanine synthetically, the amino acid. Because if you start with propanoic acid, brominate the alpha carbon, and then just do an SN2, you get alanine. So you can actually, it's actually a pretty useful way to make alpha amino acids, depending on what your starting material is. If there was a benzene ring attached here, you got phenylalanine, and that opens up a whole bunch of other things as well in terms of neurotransmitters or pharmaceuticals and drugs, all that good stuff. So it does wind up, that's why it's as niche as it is still taught because it actually does have a practical purpose. As far as what I was looking for here though, just put the bromine on the alpha carbon. Like I said, I think I asked this question out of order because it's really an alpha carbon question. And we had not gotten to that question yet. And just because I think you'd appreciate it. Hell's full name is Carl Magnus von Hell.
Amazing.
Which you can't, like that's such a like German name.
Yeah.
That is a name, right? It feels like we're doing a deep dive into the lore of Warhammer. Yeah. Could very easily be, a relative of somebody in Warhammer. Anyway. So it turns out we can also do these condensations, these alpha carbon condensations with esters. Right, and so this one is gets its own name. This is a Claisen condensation. And so Claisen condensation, if you start with the ester and you expose it to a strong base, typically you want to use the same base as the other side of the ester, as the leaving group from the ester. So that we get, so that we do go through a carboxylic acid substitution, it'll be the same molecule, just like we said before with the hydroxide. So strong base that matches your leaving group here, it's gonna deprotonate here. And if you have another molecule of the same product here, you can wind up with it attacking the carbonyl carbon. So you get the alpha carbon from one molecule attacking the carbonyl carbon from the other one. So really similar to our aldol condensation. The difference is, just like with before, the difference between all of the aldehyde ketone reactions and the acid derivative reactions is, instead of bringing the carbonyl bond permanently, it'll go through an intermediate. It's going to look like and this is the alpha carbon. There's the carbonyl, and then there's the other side. There's some methyl on there as well. Make sure you cut the carbons right. So if this was the aldol condensation, we would just protonate and we'd be done. But because it's a carboxylic acid derivative, what's different about carboxylic acid derivatives compared to aldehydes and ketones? What allows us to convert back and forth between them? A good leaving group. So we wind up reforming the carbonyl, and your leaving group leaves. So I drew it backwards from the way it's drawn here, but it's the same molecule, right? One carbon, that's our methyl, then our carbonyl carbon, then the alpha carbon to the rest of the molecule, and then the starting molecule. So our starting, there's our starting molecule. This is what's left of the second starting molecule, ethyl acetate. So really close to the same mechanism. Also, I meant to mention this before we got into the new material. I did see your question, David, about how do we keep all this synthesis pathways straight?
Yeah.
Basically group them by reaction group.
Yeah.
I'm gonna look to see if I can find a decent PDF or figure.
Yeah.
That kind of tracks all of them, but really there's so much we've covered. To try and put it all into one figure is almost impossible at this point, right? How do you reduce an entire year into one figure that's actually legible? So it's one of those things where if you have a general reaction map, like, okay, I know I can go from a carboxylic acid to an alcohol, but I know that there's some extra details there that I didn't put on my figure.
Yeah.
So then you go back to your carboxylic acid chapter and refresh your memory, or you go back to your alcohol chapter and refresh. You kind of have to like think of it as nested information. The deeper you go, the more there is.
Is there any good like practice proposals for that then? Like,
I started looking around on break, and I did see that Master Organic Chemistry has a PDF for sale. It's a 15-page PDF with 27 individual reaction maps based on key functional groups. And there's it's $15. I'm not sure if it's worth it or not. But here's an example of the page on alkynes.
Okay.
It's like, okay, well, here's our terminal alkyne, from terminal alkyne, we can go to this, so if we do this route, we can. Reduce it to the enol, which then turns into the alkyl, like,
Yeah.
it has more details, it's the zoomed in version.
Yeah.
So if you had like the free compound chemistry version of, here's all my major reaction groups, and here's how you can get from one to the other, but without all the details, and then you had some. You know, there's like. You know, you could do one of those for every single chapter we've covered practically at this point, right?
Yeah.
So I'll see if I can find a free resource or something that kind of has a good balance between detail and readability.
Yeah.
But I don't have anything on hand. Because it does start getting to be a bit of a lot, huh?
Yeah, and lately I've been studying the native influence classes, now that's over, so I'm like, I have time, but I need to get all of this straight in my head now.
And it's one of those things like synthetic organic chemists, you spend enough time in this, it becomes your native language, right? And then it becomes like, oh, of course, that's the Zelinsky full heart reaction. Do you remember that? Yeah, it's, but it just comes with time and immersion. Put in your 10,000 hours. So this is the cleaner version of the Claisen condensation mechanism. Start by making your enolate. Your enolate then attacks carbonyl makes that tetrahedral intermediate, which then kicks off a leaving group.
Yeah.
And then you can wind up with it. Then you will wind up making this doubly stabilized enolate, like we've seen before, because we still have this leaving group around, which is a strong base.
Yeah.
So then that does open it up into polymerization reaction. The other thing that it opens it up to is you're not really going to see a dehydration so much here, but basically once you get here, then you just add some water to it, add a proton source to get your final product, which is our step 2 right there. All step 2 is doing is neutralizing the combination of the alkoxide and the enolate that you make as your product. All right, so this is actually a pretty straightforward one. What base would you use? Both of these cases, they're Claisen condensation, so you're going to get 2 of these molecules and stick them together.
Yeah.
So what base do you use for step 1?
An AOET.
Yeah, you want to use the same base as your leaving group. Right, because that limits that secondary reaction. That's easy enough here, NaOET. TB okay? Was there anything about this mechanism, anytime we use TPOK, it always makes me think about steric considerations, right? Is there anything about this mechanism makes you think we have to be worried about sterics? We do need access to the alpha carbon, but other than that, there's not really anything else that it can attack, right? This is our starting material. What else is this TPOK going to, where else is it going to find a hydrogen other than the alpha carbon? And the alpha carbon is not that sterically in. All right, let's try drawing the products. We'll start with these big esters. When they go through replace and condensation, what do we get? Okay. As always, the trick is don't lose any carbons. Unless you need to lose them. So you can start by drawing your initial molecule, and then on the alpha carbon, you attach a carbonyl carbon. And the other side of that carbonyl carbon is whatever was part of the initial ester parent molecule. You get, so basically we're attaching this, everything but the leaving group gets attached to the alpha carbon of the parent molecule. I think I got everything there. Also starts to make sense why both chemicals and food have a shelf life. Because there's so many reactions that can happen. This one needs a little bit of a base to get it started, but it's pretty easy to see that a lot of molecules can react with themselves under the right circumstances, and the right circumstances are frequently just you have some oxygen or you have some water. Which is why the absolute best thing you can do for your shelf life of anything, be it pharmaceuticals, food, other chemicals, is remove all the air, remove all the water, seal it into an airtight, watertight container, and then put it in a freezer. When you do that and stuff, unless it gets freezer burnt, if you put it into a chest freezer and never open that chest freezer, there's a decent chance it'll last forever. Well, within 6 weeks.
It'll last as long as the power's on.
Yeah, sure. If I was distilling this down to a process, say draw your starting material. Find your alpha carbon and draw a new bond to it. And then it really helps me to circle the part that I'm then adding. So circle everything except your leaving group. And add it to the new bond you drew to the alpha carbon. And we really don't want to get involved theming this.
No, not particularly.
Okay. Good.
I'm trying to think of even what the prefix is for ketones off the top of my head. I'd have to look it up myself. I know we could handle naming this if we didn't have that second functional group there.
Yeah, I don't see that. Yeah.
Methyl 1, 2, 3, 4, 5, 6 methyl hexanoate. But then you've also got a dimethyl and a in parentheses dimethyl ethyl attached. And then you've got that. It's not a carbonyl, it's not it's not carbaldehyde. It's not carboxy. Beside the point, that's what it is. Carbone, maybe?
So,
Oxo. Yeah, it's oxo. So, us putting all the time into learning the IUPAC naming system means it doesn't take that much to get us to the point where we could name that if we decided it was worth the trouble.
yeah.
If you want a glimpse at how far you've come, talk to Atticus about how he feels about IUPAC.
Oh, he does not like it.
He does not like.
He's not happy with it. We're gonna right now. He can't relax.
Amazing.
It's exactly what I told you. Engineers don't like OCA because you can't map your way through.
Yeah.
No.
All right, this last one. Parent molecule. There's our alpha carbon, so there's our new bond. That's gonna be all of this that gets added, starting with the carbonyl. So 1, 2, 3, 4 more. And then on the 1, 2. Right there. Always helps to sort of clean things up sometimes so that everything looks as close to 120-degree angles. Make it look a little neater. One and down count your carbons. 1, 2, 3, 4, 5 plus an ethyl group. 1, 2, 3, 4, 5 plus an ethyl group. So after we introduced aldol condensations, the next thing we did was how do we do a directed aldol condensation, right? So we can also do a cross-Claisen condensation. I don't know why they're mixed aldol condensation and a cross-Claisen condensation, but here we are. If we want to do a cross-Claisen condensation, we have the same two options as aldols. Either have an ester that doesn't have any alpha carbons, or at least not any alpha carbon hydrogens. Or you use LDA and you sequence it. And this is one of the reasons why LDA is favored for these reactions, is because it's not a good enough nucleophile. Remember, it was a sterically hindered strong base. And so it makes for a really good way to make these enolates, because you don't have a nucleophilic addition or substitution competing. So you deprotonate your first ester. This isn't technically an enolate at this point. Because it's not an aldol, or it's not a ketone or an aldehyde, but we still refer to it as an enolate. Anytime you deprotonate that alpha carbon, we'll call it an enolate, even though it's technically not the same thing. Because it reacts similarly enough. Once you make the enolate, it attaches here, which makes an intermediate where everything is attached, but then you follow that up when your leaving group leaves and you reform the carbonyl. If you wind up with a molecule where your alpha carbon is 5 or 6 carbons away from another carbonyl, a diester can go through a Diekmann cyclization, make a cyclic beta keto ester. Which is exactly like it sounds, a mouthful. Right, so it's the same thing we were doing with our aldol condensations earlier, right? Just in this case, it's the two esters reacting with each other, but they're not going to react unless you have a fairly strong base present to start the process, because we do need to deprotonate the alpha carbon for this to happen. So you start by deprotonating the alpha carbon that attaches here. Then we get a 1, 2, 3, 4, 5-sided ring with our ester group hanging off the side of it. So our intermediate in this case would look something like this. Kick off your leaving group, reform the carbonyl. So, am I going to test you on knowing what the Diekmann cyclization means? Absolutely not. I don't care if you remember what it's called. More interesting, can you remember that two esters, when exposed to a strong base, especially when that base is the same as your leaving group, are going to go through some alpha carbon stuff. Sense of everything else we're talking about? Follows the patterns, more of the same, right? We now have enough volume of knowledge that trying to apply new concepts to all of the knowledge we already have gets to be a bit overwhelming sometimes, but it's all repetitive.
What's the word called hydration again?
Exactly, the further back we have to go in the memory banks, the more you might need to go revisit your notes. If it makes you feel any better, I've taught this class for a long time now. It's been a while since I've taught it, but I've taught this series off and on since 2012, and that was after taking the series and then taking the advanced organic and going to grad school for organic. And while I can teach Gen Chem, throw me into any Gen Chem lecture with zero prep, and I can teach it off the top of my head. Can't do that with OChem. Once you get past the first quarter or so, you gotta go back and review it, just because there's so much to share.
And then with our final, is that gonna be mostly focused on the second half of this quarter?
Yeah.
Okay.
Yeah, because I don't expect you to have everything memorized. Like, the basic stuff, I still expect you to know what all your functional groups are. If I say ester, you better be able to draw an ester.
I don't hope so this way, so much.
I mean, we've gone over almost hundreds of reactions.
Yes.
Yeah, and if we just look at
Even have to make a 30-page, you have 5 hours cumulative final.
but what, let's see this cheat sheet, we finish this chapter. That will have been through 1,007 pages of the textbook this quarter. So, yeah, it's kind of a lot of stuff.
Oh my god.
Which is why I don't feel bad cutting lectures short this quarter, because we've put in the work.
Yeah, we put in.
All right, so with that in mind, we'll do the top two on this one and A over here, and we'll do the other ones for our review on Thursday, beginning of class. Very good. And so if this is the bond we're making, if we slice that in half, side that has the alpha carbon attached is the one you started with doing LDA. And that's the one that's going to turn into our nucleophile. So we had that ethyl propanoate. Plus LDA is going to give us our deprotonate our enolate. Then we're gonna expose it to really any sort of benzyl ester. We don't have to keep, because we're doing this one in sequence now, we don't have to keep it with the same leaving group. But for simplicity's sake, we might. So ethyl benzoate. The alpha carbon from the first molecule reacts with the carbonyl carbon for the second. We get our glazing condensation.
The three everything also work if we use benzaldehyde, because we're doing the LDA first.
If you do this with benzaldehyde, you're gonna get an OH group here instead of the carbonyl. And then you wind up with the dehydration happening to get that. Yeah.
Okay.
And actually, you will want to use the same leaving group in this case, because we still have to deal with the fact that we could wind up getting other products. Because we're gonna kick off this as a leaving group. So if this is not the same leaving group as here, you could wind up with it with a methoxy group being attached here instead of the ethyl or something like that. So you are gonna want to keep it consistent.
I'm glad I asked, so I forget that.
Yeah. That's class 1 versus class 2 carbonyls, right? Is that leaving group being there? So you get substitutions instead of additions.
Yeah.
So same starting material for B. And because we get the same piece attached to the alpha carbon, everything attached to the alpha carbon looks the same. Just that the second step is gonna be ethyl methyl propanoate. One, two, three. OET, methyl right there. Also, just a reminder. That's just so weird, they're just showing you both ways you write, that's just another way of writing ester. When you're short on space and you don't want to show the carbonyl. COO and then another alkyl group attached. We'll cover those on Thursday. So for A goes through an internal glazing condensation, aka Diekmann cyclization. So the first step is you deprotonate the alpha carbon, which then attacks the carbonyl, and we're going to chop that off. So we're going to start drawing the part of the molecule that doesn't change. Get a new bond. We are going to wind up with a 7-sided group. 1, 2, 3, 4, 5, 6, 7.
Like truly big growing maintains.
You just add another carbon in the middle. And then with a carbonyl attached. And we lost the ethyl group there.
Yes.
So if we really wanted to clean things up. See if I can do this. Not perfect, but I'm calling that a win.
Good enough.
Although now I'm thinking I added an extra carbon in there.
Yeah.
Yeah, I did.
Oh my gosh. There you go.
No, I just redid the same thing.
Boom.
And the main thing is that it doesn't have to look regular, it just has to be such that I can count all the vertices.
I'm also just gonna start on those writing 7-sided ring with an arrow pointing to it.
When I didn't set myself up for success by starting here, best way to draw a 7-sided ring, freehand, is to start with the top of a hexagon and then draw the bottom of an octagon. And then just connect them.
Oh, there you go. Alright.
It hurts, but it works. All right, so we'll end there for today. Preview of what we're gonna do next time, since I did actually have a slide, is what if we used an enolate as a nucleophile when we have a good leaving group? So also really similar, it's just gonna go through an SN2 instead of a carboxylic acid substitution.
Easy enough.
So
That's what we.
that's probably more helpful in terms of synthesis, because that's a way to add anything with an alpha carbon to anything with a halogen on it. So you can do 2 parallel syntheses and then put them together at the very end.
And that's kind of similar-ish, it's the idea of the whole like BRT, PBR thing, like it adding there.
Right,
Because that's like, instead of an RX, it's a XX.
right,
Kind of different cycling mechanism.
exactly. Okay. All right, then let's go ahead and break then.